All right, guys, this lesson from calculus is from 1.1. If you're in pre-cal, this is an intro that we do in addition to the work that we'll be doing afterwards. So to begin with, calculus, the reason we need calculus, it's because it is called the math of change. So everything you've learned up until calculus pretty much works in a linear sense. And you'll see that when I talk about derivatives more. In reality, we don't always go the same. Like if you're driving your car, you don't always go 50 miles an hour. You might slow down and then speed up. And then when you come up to the stop sign, you stop all the way and things like that. So real life has changed. It doesn't always go at a constant quantity. So that's why we need calculus. The first thing we learn about calculus is more of a conceptual thing. Mathematically speaking, it is one of the easiest one. It's very algebra based. But a lot of times students have trouble conceptually understanding it. So limit addresses the question of where am I going? And you'll see the word approaching come up a lot. It'll even be when you say the question, you'll say the word approaches every single time. Okay, so I want you to think of it as a journey, not necessarily the destination, because a limit could exist whether a point exists or not. The question just asks you where would the function have gone, whether the point exists or not. Okay, not that it has to be for points that don't exist. It could be for either. So if you take a look at these two images that I drew for you, let's first look at what the notation of a limit looks like. The limit as x approaches 3 will equal 1. So as I approach on my function 3, my y value will be 1. And notice that that statement is true for this function that is continuous and for this function that is not continuous and has a hole. Okay, so again, it doesn't matter whether the point exists or not because of the keyword approaches. It says, as I approach 3, I will be approaching 1 on the y. So derivative is a synonym for the word slope and also for the words rate of change. And I underline change there because that's the whole reason why we need to learn it, is because calculus is a math of change. So back in algebra, the way we analyze slope was by rise over run. Now, rise over run only works for a linear function. The moment you have anything that's curvy, rise over run will only give you an estimation. Again, which is where calculus comes into place because it'll give you the exact rate of change, the exact slope, but now it'll give you a slope for the bottom of the curve and a slope for the higher part of the curve that might be steeper and so on. You can find a slope for every different part of the curve. So, for example, if I look here, my rise over run is 2, right? And for this function, it will always be 2. But in real life, again, if I'm accelerating in my car, my velocity is going to increase. In real life, do you always speed up at the same amount when you're driving? No, you speed up. You kind of keep a tempo and you go the same speed. And then maybe you see the popo, you slow down a little bit. You're like, oh, I don't want to get pulled over. And then you speed up again. Or then you see a red light and then you stop all the way. In real life, we start changing that velocity. Does that make sense? So if my slope here will always be 2 over 1, let's look back at this parabola for a second. Do you agree here that my slope is negative going downward? And then do you agree that there's a point where my slope is going to be 0? And then my slope will end up changing to positive and then a bigger positive and a steeper positive. So in calculus, at every single part of the function, we can find a different slope. Okay? And that's what the procedures of derivatives will do for us. Okay? If any of you have taken physics, you've probably heard the word velocity and acceleration used a lot. That is very heavy in derivatives. Okay? I think many of you in physics do it algebra-based. You'll learn how to do it calculus-based, which is, believe it or not, a little faster. Okay? All right, the third topic, which for my pre-cal students you won't see till next year, integration is the inverse operation of derivatives. So remember, back in middle school, you learned like the opposite of addition is subtraction. The opposite of multiplication is division. The opposite of derivatives is integration. It is the undoing. So the nice thing about that is that once you learn how to do the rules for derivative, the rules for integrals is going to feel easy because you're just learning to undo the rule. Okay? Now, integrals find us total amounts. Okay? So living in Miami, I'm going to give you a picture you can all probably relate to. If you've ever been on a boat, let's say we're in the Keys or somewhere in Miami, and we're on a boat. And let's say we're traveling 30 miles an hour, and we travel from 1 p.m. to 3 p.m. How much did I travel? What did you do to get 90? Okay, be careful. It's not to 3 because I didn't start at noon. I started at 1. From 1 to 2 and then from 2 to 3. So 60 miles, right. So if I traveled for 2 hours, 30 miles an hour, what did you do? You multiplied, right? You said 2 times 30 gives me 60. That is the total amount of miles that I traveled in that time. Okay? Now, let me make that connection visually and also geometrically. What shape is made here? Some sort of a rectangle, right? If it was perfect, then we could have called it a square. So, do you agree that you technically just did the area base times height underneath that function? Yeah? So, a very key pivotal point of learning integrals is understanding that what you're doing mathematically is finding the area under a curve, and that number of the area under the curve will give you the total amount of quantity, whether it was how much you traveled, or if you're talking about a company, any of you who plan on studying business, you can find total amounts that the company sold and things like that. Okay? So this is very elementary level, because in our boat, do we always go 30 miles an hour? No, right? We take off, we increase our speed, we kind of plateau, and then when we're pulling back into the dock, we slow down, right? So we will learn how to find areas under curves that are functions that are curvy instead of just linear, okay? And our very last topic that we learn in calculus is series. Series is a topic that is only taught in AP Calc BC. It is the topic you learned at the end of that course. So if you're in AB honors or learning this at the end of pre-cal, you won't see that for a while. But if you've ever seen anything in stats or probability, like in trigonometry, some of you who took that, we started seeing like these patterns of numbers that make a series of numbers. And in calculus, we start seeing what happens to those series of numbers as they start to approach infinity. Okay? All right, so now we have to go over some things that you need to remember from algebra that will pop up throughout these calculus questions. In my personal opinion, the actual calculus you'll learn is not the difficult part. It's being able to recall all of these old algebra concepts and your unit circle and things like that. So if I want to expand a binomial that's squared, the biggest mistake I see is that people square A and square B. Please remember that that 2 represents 2 of these. You can write 2 of them in FOIL, or a shortcut is to remember that it will always give you A squared plus double A times B plus B squared. Okay? And an example we can see about that one is down here. So again, you could write 2 of them in FOIL, or you can remember that it's going to be the first term squared plus 2 times the first term times the second term plus the second term squared, which that's going to give me 4x squared plus 2 times 2 is 4. 4 times 2 is 16 with the x. And then plus 4 squared is also 16. Okay. The next one to remember, these are called sum and difference of cubes because they both have cubes. Okay. So the first binomial has an A and a B. I'm going to ignore the signs for a second. Then you have the first term squared, each term multiplied, and then the second term squared. Now, that part is the same for both. And then the way I remember the signs is with the acronym SOAP. And that stands for same, opposite, always positive. So if I have plus, I have the same, which is plus, opposite, and then always positive. If I have minus, I have same, opposite, and then always positive. Okay? So 2 examples of those. Here is to realize that you are working truly with x cubed plus, what number would make 8 cubed? I'm sorry, what cubed would make 8? 2, exactly. So it's plus 2 cubed. So my b is really 2. So this expands to Same sign, x plus 2. Now x squared, opposite sign. Multiply them together. And then always positive, the second term squared. Okay? Now let's do the same thing with a subtraction. This is truly saying x cubed minus what cubed? 3 cubed, good. So now I have the x and the 3. Here's how you do it if you don't want to write the signs yet. Then you have x squared, 3 times x, and 3 squared, which gives me 9. My signs go same, opposite, always positive. And then the last one of my, I don't want to say my favorites, but it's the one that I see the most often come up. And that is called a conjugate binomial. And that is when you have a squared minus another squared value. All right, a student just drew to my attention that I accidentally put a squared here instead of a cubed. All right. So back to this question. Do you see that I have a squared minus a squared? What squared would make 9x squared? 3x. If I square 3x, then that gives me 9x squared. Minus, and what squared would give me 16? 4. Okay, so for that reason, I can put the first term and the second term, one with a plus and one with a minus. So I could put 3x plus 4 times 3x minus 4. Okay? And lastly, factoring, which is definitely the one you will see the most. You want to find two binomials that will give you that trinomial. So what two values do I have to multiply to get an x squared? X times x. And how about two values that multiply to give me -6, but combine to give me -1? Right, so I have 2 times 3. And then if I need a negative number, I need my bigger value to carry that negative. Okay, so the bigger value should always carry the sign that you want for the middle term. So the next part that I need you to remember, and this will come up a lot, especially in limits, is functions and their continuity. So remember the main types of discontinuity visually on a graph? We had holes, asymptotes, and jumps. The main function that we see discontinuities are rational functions, which are fraction functions. So you have a numerator and a denominator. Okay? So the way you find where a function is discontinuous is by setting the denominator equal to 0 and solving for that x. That x value will show you where the function has a discontinuity. Okay? Now there are two types of discontinuity, removal and non-removable. Okay? So if the portion of the function can be reduced, that portion that got reduced is called the removable discontinuity. Okay? And on the graph, that makes a hole. If you want to know where to graph the hole, you have to find its y value. You do that by plugging that x value that you found for the hole into the reduced portion of the function. Okay? If there is a portion left in the denominator that did not get reduced, that is called the non-removable discontinuity. And that's what gives you your vertical asymptotes on a graph. We are going to do an example of each of these, okay? So bear with me if you don't remember exactly how it worked algebraically. The next type of discontinuities are horizontal asymptotes, okay? When you have your fraction function, you need to look at the leading terms. Do you guys remember how I determine who the leading terms are? It's whoever has the highest exponent, okay? So I'm just going to pick the term in the numerator and denominator that has the highest exponent, and I'm going to compare their exponents. So n and m represent exponents, and a and b represents coefficients, numbers being multiplied, okay? If the exponent in the numerator is greater than the one in the denominator, then there is no horizontal asymptote. If they have the same highest exponent, then the horizontal asymptote is located on y, because it is horizontal, at a over b. So whatever those numbers give you divided, okay? And then lastly, if the exponent in the numerator is smaller than the one in the denominator, then my horizontal asymptote is at y equals 0. A piecewise function is the last one we're going to look at. Now, this one is probably the one you are least familiar with, but it is probably one of the easiest to do, okay? A piecewise function has a bracket with several functions given. Now, each function has a restriction of its domain, meaning like of where to draw it. So all this is, it's literally pieces of functions that you're all putting onto the same graph, okay? So let's take a look at what these look like. Okay, I've got 3 examples for you, and then we'll be done for today. So, example number 1. The first step you're going to want to do is see if you can factor out or expand these functions. So, based on what we saw earlier, and you can refer back to your notes, we saw that x cubed plus 8 was a sum of cubes that expanded to x minus 2 times x squared minus 2x plus 4. And we also saw earlier that you can refer back to your notes that that denominator can be factored into x. Oops, I made a mistake here. This is a plus. X plus 2 times x minus 3. Okay? Now the denominator set equal to 0 is going to give me my 2 discontinuities. Okay? Do you see that one of those 2 binomials can get reduced? Do we see that? Okay. So the one that can get reduced, we said is a hole in the graph. It is called a removable. So we can go saying that my hole will be found when I set that denominator equal to 0. And that yields me to the hole being at -2. Okay? Now, the portion in the denominator that did not get reduced will give me my vertical asymptote. Okay? And I find the location of that by setting that denominator equal to 0. And that'll yield to the vertical asymptote being at +3. Okay? Now, these are things we can go placing on the graph. I need to find the location of that hole because the vertical asymptote is going to be easy to draw. I could just put my line all the way down. Okay? But my hole, I know it's going to be somewhere on -2. I need to find where. So, I know that my hole, we said we find the location of the hole by plugging the x value into what's left over. Okay? So, I have to say -2 into this leftover. So -2 squared minus 2 times -2 plus 4 over -2 minus 3. Okay? You should get 12 over -5, which that gives me about -2 and change. Do you agree? Okay. So if I told you the x value is -2, we just found that the y value is -2 and change. You don't have to be perfect. This is just a sketch. So that's where my hole is going to be. Okay. Last part. Check for a horizontal asymptote. Okay. The horizontal asymptote is easiest to look at the original because that's the easiest place to find who the highest exponent was. Who was the highest exponent in the numerator? 3, right? So I'm going to write that term, which was 1x cubed, over what's the highest exponent in the denominator? 2. So I'm going to write that term, which is 1x squared. According to our rules, where is the exponent greater? In the numerator, which what does that mean? There is no horizontal asymptote. Okay. Now, I definitely know that this function, remember in the beginning of the school year when we practiced our functions, we said fraction functions gave us the elbows look. We remember that? So I definitely know that this elbow is going to have to approach the asymptote. So I know for sure this one is down here. Okay. I might want to know where the one on the other side of the asymptote is. So with that being said, you can pick any x value over here, even something as simple as 4, and plug it into the function to figure out where that's located. Okay? So if I plug 4 into my original function, okay, you can plug it into the original or the reduced and it should give you the same exact thing. What is 4 cubed? It's 64, and then plus 8 gives me 72 as my numerator. And now I have 4 squared, which is 16. Minus 4 is 12. Minus 6 is 6. So 72 divided by 6 gives me 12. That means at 4, I am way up high at 12. Okay? It's past what I drew. That means it's going to come down really close to the asymptote, and then somewhere it's going to shoot out. Okay? Are we ready to go to the next? Okay. Oops, I skipped it. Sorry. So the numerator on this question is already simplified as much as possible. It says x minus 4. Okay. The denominator can be factored out. I need two numbers that multiply to give me negative 8, but combine to give me a negative 2. What two numbers are you coming up with? 2 and 4. And I need this value to be negative, so who gets my negative? And 2 gets a positive. All right? We see how this x minus 4 cancels? This is going to work out just like the last problem. I know that my whole is going to be found when I set x minus 4 equal to 0, which tells me that my whole is at positive 4. Let's take a moment and find the location of the whole. So the whole is going to be me plugging 4 into the leftovers. Remember that when I reduce, what I get in my numerator is just a 1. And then I plug that 4 into the bottom. Okay? Which gives me 1 over 6. That means my whole is going to be really close over here at 4. And let's call this one just to give us some more room. And that means if this is 1/2, 1/6 is probably somewhere down here. That's where I'm going to draw my whole. Okay? Now let's find, we do have something left in my denominator after I reduced. That's going to give me my vertical asymptote. I find the location of that by setting that equal to 0. My vertical asymptote is over here at negative 2. Okay, and let's shoot out this line a little more. And now horizontal asymptote. Look at my original. What's the highest exponent in the numerator? So I use that term, which is just x to the first. And then my highest term in the denominator, right? So I use positive x squared. Whose exponent is bigger? Which means, good, since the denominator's exponent is bigger, my horizontal asymptote is at y equals 0. Okay? So that means I'm going to draw an asymptote all the way along y equals 0. So far, this is the example I told you has a horizontal asymptote, a vertical, and a hole. Now, this is an elbows graph, so I definitely know that the elbows on this right side is going to be up top. I could tell by the hole. And then if I want to check where the elbow is going to be on this left side, whether it's on top or the bottom, I just plug any number on the left side of this asymptote, so I can put in -3. And so since last time we plugged it into the original, I'm going to plug this one into the leftover so you can see how it works the same. I can say the function at -3, I'll plug it into the reduce, which would give me 1 over -3 plus 2, which that gives me 1 over -1, -1. Okay, so I know that dot is going to be right here, which tells me that this elbow goes this way. Okay, oops, sorry about that. And lastly, let's look at our piecewise function. So let's take a look at this last question. It is our piecewise function. So as you can see, I have a bracket with 3 different functions, and each function has a domain restriction. So I'm going to start off with a pencil. The graph of x squared plus 2 is a parabola that was shifted up 2. Okay, so if I draw that whole image, it looks something like this, right? That's this part, this left side. Now with my pen, I'm only going to mark the portion that agrees with this right side. It says only allow that parabola to exist when x's are less than 0. Okay? Remember your inequality signs. If it just says less than, that means I do not include 0. If it says less than or equal to, then it means I do include that value. So if I put my pen on 0, and it says x is less than, am I going to let exist the left side or the right side? The left side. So I'm going to put a hole at 0, and then I'm only going to draw that left side. Okay? And then I'm again, you won't need to do this once you get good at these, but then I'm going to erase the right side, because it only wants me to let it exist on the left side. Is that making sense so far? Okay. Now let's go to the second function. What is the graph of x plus 2? It's a linear function with a slope of 1 that moved up 2. So if it moved up 2, it's going to go from here, and it's going to go rise 1, run 1, rise 1, run 1, and it's going to be a linear function in both directions. Do we agree? Now with my pen, let's look at my restrictions. It says it wants this line to only exist between x equals 0 and x equals 2. It says include the 0. So I'm going to fill in 0. But then when I get to 2, do not include 2. And only have it exist in between x equals 0 and x equals 2. Do we see what I marked in blue? Okay, now I can erase the rest, because it only wants it to exist in that portion. Okay? And now the last part. The function of f of x equals 4 is just a horizontal line at y equals 4. Okay? So, y equals 4. Let me get my pencil. If this is 4, it is just a line that exists all the way through 4. Agreed? Now, the domain says just to let it exist when x values are greater than 2, but not including 2. So here's 2. It says not including 2, but greater than. Am I going to keep the left side or the right side? The right side. So with my pen, I need to keep the bubble because it never asked me to underline the 2. I'm just from that bubble going to go on to the right. And then erase the rest. Okay? And that is the sketch of your piecewise functions. Again, pieces of those three functions.